Welcome everyone. This is separation processes course. Today we are going to take an example for the topic that we have discussed, which is the multi-stage, multi-component distillation. So this is the example. Let's say that together a distillation column. So we have a distillation technique has a feed of this is the total feed 100 kilomole per hour, and the feed is 50 more percent of the light non-key, 50 more percent of the light key, and 35% of the heavy key, and it seems there is no heavy non-key, and it is saturated liquid. And when we see that it's saturated liquid, we need to know that Q is equal to 1 as the saturated liquid. The reflux ratio is 1.2 times the minimum, okay? And we desire to have 99.5% recovery of the light key in the distillate, and the mole fraction of the light key in the distillate should be 0.75. So the first one he gives me fractional recovery, and the second one he gives me the composition in the distillate of the light key, which is 0.75. Assume that the light non-key is 100% recovery, of course in the distillate as it is light non-key. Use FUG approach. Why you are using this FUG approach? Because we have a multi-component, more than 2 components. Of course it can be used for binary mixture also, but when there's more than 2 components, we have here light non-key, light key, and heavy key, 3 components. That's why we are going to use this FUG approach. So part A, this is an example that covers everything, approximately everything that we covered last video. So in part A, he wants me to determine N minimum. Part B, he wants me to determine R minimum. Part C, the number of ideal stages, theoretical stages. And part D, the optimal location of the feed. Okay, so part A we can use, it is FUG, so part A N minimum is Vensky, part B R minimum is Underwood, part C, that's number of stages, it is Galilean, and part D, which is the optimal location of the feed, we are going to use Kirkbride correlation. And he gives me some equilibrium data that the distribution coefficient for the light non-key is 4, distribution coefficient for the light key is 1, distribution coefficient for the heavy key is 0.75. And this is a fractional recovery. It's defined as this, dxd over fxf, as we discussed before. Okay, so the first thing, before we are going to solve anything, we are going to list the given information. The first information that we have is, first information is we have 100 kilomole per hour feed, and we have the composition in the feed of the light non-key. And what I mean by light non-key, and it's like this: you have this distillation column, you have the feed, and it is a condenser, and this is the reboiler, and we have here the feed, and we have here the light key and the heavy key. The lighter than the light key is the light non-key. Okay, so these are my components of interest, the light key and the heavy key, and the lighter than this light key is called light non-key. And the composition here, z value composition here in the feed are given as such. In the problem it will given that for the light non-key in the feed, so when I say z, I'm referring to the composition in the feed, it is 0.15, and it was given zlk for the light key, it is 0.5, which is 50%, and lastly z of the heavy key is 0.35, and of course summation of all the compositions should be 100%. And also he said it is a saturated liquid, that's why Q is equal to 1. Okay, and also he gives me that, what else? He gave me an R equal to 1.2 R minimum. Okay, and he gave me the fractional recovery. Fractional recovery of the light key in the distillate is 0.995, which is 99.5%. And also he gives me X on X in the distillate of the light key is just 0.75. Okay, and as we assumed before, that this light non key, as it is lighter than the light key, it will be recovered totally at the distillate. That's why he mentioned this information, that we have 100% recovery of the light non key. So we recover 100% of the light non key in distillate. All of this light non key will be recovered here, and there will be no light non key here. Okay, and yeah, and also he gives me equilibrium data. This the K distribution coefficient for LNK and for LK and for HK. Okay, these are the distribution coefficient values. So the first thing that I prefer you to start with is start finding the relative volatility values, the alpha values. Okay, and you know that alpha I is, yeah, alpha for any component I is the distribution coefficient of this component over distribution coefficient. We refer everything with respect to the heavy key. So this will be the distribution coefficient of the heavy key. Okay, we refer everything to heavy key. Okay, so start finding this relative volatility, and as we have three components here, so we will have three relative volatility values. Okay, so first the relative volatility for the light non-key will be k of this light non-key over k of heavy key, and they are given in the problem, right? Here, this is k of the light non-key 4 and the k for the heavy key 0.75. So you just divide them. So it will be 4 over 0.75. Okay, so you get alpha of the light non-key is 5.33. And again, alpha for light key will be k of the light key. It was given in the question, yeah? It is here, k of the light key 1 over k of the heavy key 0.75. Okay, so it will be 1 over 0.75, which is 1.33. Lastly, the alpha of the heavy key, of course, without doing anything, it will be for sure 1. Why? Because it is k of the heavy key, and we are finding the relative volatility with respect to the heavy key. So again, division by k of the heavy key. So it will be 1 always. Okay? And you can notice that the heavy key has a relative volatility of 1. The light key would be lighter, so it has a higher relative volatility. The light non-key will be even lighter, so it will have a higher relative volatility compared to the others. Okay, so this is the first step that you are supposed to do, is to find the relative volatilities. Okay, now the second step we are going to do is just material balance. It's just material balance step. Okay, it's just material balance step based on information that we have. So the first thing, we are going to utilize the fractional recovery. We are going to utilize the fractional recovery that was given in the question. Okay, so we given a fractional recovery value, so we will utilize this. Okay, so as you know, fractional recovery value of any component I in the distillate is distillate composition of this component multiplied by the total distillate flow rate over the composition in the feed of this component multiplied by the total feed. Okay, in other words, as we agreed before, this term can be written as di, right? X di multiplied by d, it is just the flow rate of this component I. And this term also can be written as fi. Okay. So what we are given in the question, we have the fractional recovery, and we have z value, we have the f value. Okay, but we don't, or do we? Do we have? Yeah, and we have also this xd. Okay, so we can easily determine this d. Okay, or in other words, we can determine di. Okay, so but what fractional recovery we have in the question? We have a fractional recovery of who? We have fractional recovery of the light key. Okay, so we have a fractional recovery of the light key. So this will be fractional recovery the light key in the distillate, we can write it as d of this light key, this one, over fi, or instead of fi we can write zif. Okay, so over zif. Okay, so we can rearrange this equation. We will get dlk is equal to this fractional recovery of the light key in the distillate multiplied by the z of the light key multiplied by f. And we know all of this. This was given as 0.995, this was given as 0.5, and this is 100. So just multiply them. So now you can get that the distillate flow rate of the light key is 49.75 course kilomole per hour. Okay, and from this we know that this distillate is equal to xdid. Okay, so we can say that this dlk is xd of the lk multiplied by the distillate. So in other words, we can say that the distillate is distillate flow rate, the total distillate flow rate for all components in the distillate is just dlk over xdlk. Okay, and this we determined already, 49.75 over 0.75. You can use the calculator, you will get it as 66.33 of course kilomole per hour. Okay, so now someone would ask why we are finding this, why we are doing this and finding this d, because we will need it later on. We will need it, for example, when finding the number of stages using the galilean correlation, we need this value of d. Okay, and someone will wonder why we are finding this small d of the light key, the distillate, because we will need it later in the Underwood when we want to find the minimum reflux ratio. That's why I'm starting using material balance and utilize every single information given in the question in order to have a complete material balance that will help me in other equations that we are going to use later. Okay, that's why I am doing this. Okay, and of course you know that f is equal to d plus w. We know f, we now know d, so we can easily determine this w. Okay, so w is equal to f minus d. This we know as 100, and this we got already here, so we can subtract them easily. We will get w as 33.67. Again, why I'm finding this w, because we are going to use it later in the correlations. Okay, and as we say that f is equal to d plus w, similarly f of individual component is equal to d of individual component plus weight of individual component. Okay, so I can find also wi. Okay, so I can write it in this way. I can write w of the light key, for example, is equal to f of the light key minus d of the light key. This one I determined before. This one I determined before. Here. Yeah, 49.75. And this one, how to get this, is simply z of the light key multiplied by the total f. I know this, which is 100, and I know this, which is 0.5. So it is 50. Yeah. So I can easily get WLK. Again, why I'm finding this WLK, because I will need it later in the calculations. Okay, so it will be this minus this. So when you subtract them, you will get a value of 0.25, which is expected to be very small. Why? 0.25 of course kilomole per hour, and it is very small. Why it is very small? Because it is light key, so it's expected to be recovered more يعني in distillate. That's why it is flow rate in the waste is very small. So it is acceptable answer or acceptable value. And again, similarly, you know that w of the lk is equal to xw of the lk multiplied by the total w. So as we know, we know this WLK, we have just determined, we know this W, so we can again get this. So this we know 0.25, and this W we know 33.67. You can plug them here and get that XW of the light key as equal to yeah, it will be very small as expected, 10 to the power minus 3. Why it is very small? Again, because it is light key, it's expected to be more in the distillate, not in the waste. That's why the composition is very small. And now it's a critical point that I want you to understand is that let's go back to the diagram. Yeah, this one. As this light key will be totally recovered here in the distillate, so what we will have in this waste? We will have only light key and the heavy key, isn't it? Okay, so you can say with a confidence, you can say that x in the waste of the heavy key will be 1 minus x of the waste of the light key. Why? Because summation of all mole fractions are equal to 1, and we have only two components in the waste, which are the light key and the heavy key, as the light key will be recovered totally in the distillate. Okay, so we know this, it is here, so we can easily get XW of the heavy key, which will be 0.9926. Okay, again, why I'm finding all of this? Because we are going to use this later. This XWHK will be used later, and everything that we calculated for material balance, we will use it later. Okay, so just preparing ourselves, yani we prepare all information that we need to use later in the correlations. Okay, now what else? Also, uh, uh, yeah, we have also we can determine also, as we know this, XW of the heavy key, and so we can determine W of the heavy key, the individual flow rate, individual molar flow rate of the heavy key, which will be just the composition of the heavy key in the waste multiplied by the total waste flow rate. Okay, so I know this, I determined before 33.67, and I know this XW of the heavy key, which is 0.9926. So I can get easily this, can get that W of the HK is equal to 33.42 kilomole per hour. Okay, uh, again I can determine DHK, the distillate flow rate of the heavy key, simply by subtracting the feed flow rate of the heavy key, or subtracting from the feed flow rate of the heavy key minus W of the heavy key. So you have this feed of the heavy key, you are removing the waste of this heavy key, so you are going to get the distillate of this heavy key. And this again we determined it before, the waste of the heavy key it was 33.42, this value, and this F of the heavy key we it is simple, we can determine it. F of the heavy key is equal to Z of the heavy key multiplied by the total feed. We know this is given as 0.35 and this is 100, so 0.35 multiplied by 100 is 35. We subtract them, we will get 1.58 kilomole per hour. Again, you need to ask yourself, is that reasonable or not? It is a heavy key, so it's expected to be more in the waste, and we are finding the distillate flow rate of individual component, which is the heavy key. That's why it is very small, because it is not its place. The distillate is not its place for the heavy key. That's why it's expected to be very small. Okay, yeah, and similarly we can determine also the XD, distillate composition of the heavy key, from the distillate flow rate of the heavy key that we have just determined here over the total distillate flow rate, which is the common definition of composition. Composition is just the individual molar flow rate over the total molar flow rate, individual molar flow rate over total molar flow rate. So since it is for the heavy key, that's why I am using the individual flow rate of the heavy key. And I know this already, this is 1.58, I have just determined here, and this is 66.3, we determined it before, so we will get that xd of the heavy key is equal to 0.024, and that's it. I think this is enough for material balance. Sorry. Yeah, that's all for the material balance. So we finish with everything that we will need in the coming equations, in coming correlations. So now we can start our correlation, and we can start part A, which is we have everything is ready, every material balance is ready, so we can go all the way and start finding the required values. The first thing is required as n minimum, the minimum number of stages, which can be used determine what can be determined using Venski. Okay, we can determine it using Venski. Okay, and what's the Venski equation? It is n minimum is equal to ln over ln, right? Ln over ln. This ln here is alpha of the light key, and this ln here is a little bit bigger. It is xd of the light key over xw of the light key divided by xd of the heavy key divided by xw of the heavy key. So I think now you understand why I did all of this material balance. The target of this material balance is that now I have xdlk, and now I have xwlk and I have xw heavy k. Let me do it. So I can directly substitute them rather than going back and forth for the material balance. I did the material balance at the start, finish all material balance that I need, then I just start plugging in the values. Okay, so it is ln over ln. In the denominator, it is the relative volatility, which we determined before as 1.33. Okay, and then this one here, it will be 0.75 over 0.75 over 7.425. 7.245 10 to the power minus 3, yeah, to determined before, over 0.024 divided by 0.9926. All of these values we determined before from material balance, so we can get that the minimum number of stages required are 29.24, which is approximately 29 stages. Okay, or 30 stages, and between 29 and 30 stages. It's just an approximate value, of course. Okay, so this is the required number of stages. Now we can move to the part B, which you need to determine R minimum. And again, how to determine this R minimum? How to determine this R minimum? How to determine this R minimum? We need to use Underwood correlation, and you know that R minimum is equal to L minimum over D. This D we already determined it from material balance, so we need to get L minimum, and you know that L minimum is equal to V minimum minus what? Minus D, yeah. Okay, we know this D from material balance again, so we need to get V minimum. How we are going to get the V minimum? We are going to use the second Underwood equation. But before, as we discussed before using the second Underwood equation, you need this phi, capital Phi. And how you are going to get this capital Phi? You need to use first Underwood equation. And what's this first Underwood equation? First Underwood equation is 1 minus q is equal to summation of zi alpha I over alpha I minus eta, or phi. Okay, so let's substitute. What's q? It is 1, and of course we have all the values of z and alphas. All values of alphas we already calculate them, so we can use a solver to get this phi. Okay, so we can write 1 minus q, which is 1, is equal to 0.15, the first z, the z of the light non-key, multiplied by the relative volatility of the light non-key, divided by the relative volatility of the light non-key, minus eta, or phi, plus zero point 0.5 multiply, which is the z of the light key, multiplied by 1.33, the relative volatility of the light key, over 1.33, the relative volatility of the light key, minus phi, plus, it's a summation, right? The last thing, it's the heavy key, 0.35 multiplied by the alpha of the light key, of the heavy key, which is 1, alpha of the heavy key, which is 1, minus phi. So just, it's the summation. Just to illustrate, this term has to do with the light non-key, this term has to do with the light key, this term has to do with the heavy key. So the only unknown here is phi, and you can see it is non-linear equation, so you could have many solutions, so you need to choose a good initial guess, and we say that the good initial guess should be between the alpha of the heavy key and alpha of the light key. And alpha of the heavy key, it is 1, alpha of the light key we determine it as 1.33, so a good initial guess would be, for example, to 1.2, just for example. Take this value as an initial guess, use your solver or a program or whatever you can use, so you will get the value of phi as 1.11. Okay, that's it. Once you get this value of phi, you can use the second Underwood equation to determine V minimum. And what's this second Underwood equation? It says that V minimum is equal to summation of alpha I di over alpha I minus eta, or phi. Okay, so we can expand this summation and say that V minimum is equal to, so let's substitute directly. Let's start, we will start with the light non-key, then the light key, then the heavy key. Okay, so the first thing is alpha for the light non-key, which is 5.33, multiplied by what's di? Di, it was 15. And how we know that? No, not from material balance, so you can now appreciate what material balance that we did before help us now at this stage. Over again alpha I, which is 5.3, minus what's eta? We determined it already as 1.11. 1.11. Then again, so this term has to do with the light non-key. Now for the light key, it will be what's alpha? It's 1.33. And what's di? It is 49.75. We determined before from material balance. And over what's this alpha I? Again 1.33, minus what's phi? It is 1.11. So this has to do with the light key. Lastly, for the heavy key, what's alpha is 1, what's di is 1.58, which is again we determined before from material balance, over 1 minus what's eta, or the phi, it is 1.11. Okay, so you can use a calculator to get a value. So using calculator, you will get a value of 304.3 kilomole per hour. So this is your V minimum. This is your V minimum. Okay, so again, this term has to do with the light non-key, this term has to do with the light key, this term has to do with the heavy key. Okay, and then, but do we want this V minimum? No, we want R minimum. So we will do step by step. We have V minimum, subtract D, you will get L minimum, divide L minimum by D, you will get R minimum. Okay, so let's do it. Let's do it. Okay. So we can say L minimum is equal to V minimum minus D. Okay, and we already know this D, we determined before from material balance earlier, so it's 6.33, and we just know this V minimum. Here you subtract them, you will get L minimum equal to 237.95 kilomole per hour. Okay, 237.95. Then you want R minimum, which will be L minimum over D. You just divide this by this. Okay, so it's a simple division. You will get R minimum is 3.59 or something close. Yeah. Last thing, uh, you know that it was given that R is equal to 1.2 R minimum. So if you know R minimum, you can get the actual reflux ratio. If you multiply these values, you will get the actual reflux ratio as 4.31. Now the part C, it wants the theoretical number of stages. So are you going to use Galilean? And in order to use Galilean, we need to find first x. And what's x? It is R minus R minimum over R plus 1. You know R minimum, you know R, you can find x, so x will be 0.134. And then you can use this correlation to find y, which is 1 minus exponential of this big term, 1 plus 54.4x over 11 plus 117.2x multiplied by x minus 1 over x power 0.5. You know the value of x, plug the value of x, you will get value of y is equal to 0.52. And you know that this y is equal to n minus n minimum over n plus 1. And at the end of the day, you want to get this n. You want to get this n. So you have this y, and you know n minimum from where? From part A. From where? From Venice-Key equation. You know this n minimum already. So you can use the solver to get this n. Yeah, what was this n minimum? Let me see. We determined it before. Where is it? Yeah, n minimum. This one. 29.24. 29.24. 29.24. So you just substitute n minimum here. Use your solver, you will get the actual number of stages is equal to 61.9. It's around 62 stages. This is the actual or theoretical number of stages. Now the last thing, which is part D. Part D, he wants me to determine the optimum feed location. In other words, the feed location. So we need to use the Galilean. We need to use the Galilean correlation. Okay, we need to use not Galilean. Sorry, we need to use the Kirkbride or Kirkbride correlation, which is NR over NS, the stages in the rectification section, over the stages in the stripping section. And please here note, there's something I forgot to mention in the last video, that the rectification section, if you are using partial condenser, so the number of stages will be included here in this rectification section. Again, if you are using well, it is always partial reboiler, so the reboiler stage will be contained also in this NS stripping stages. Okay, so we can use this correlation. It is some big bracket to the power 0.206, and then you have ZHK heavy key over Z of the light key, XW of the light key, XD of the heavy key to the power 2, then you have W over D. Now you know what we did, all of this material balance. We did the material balance before we start anything to get this W. So we have it. We already have this W from material balance 33.67, and we already have this D as 66.33. And it is given in the question that ZHK of the heavy key in the feed 0.35, which is 35%, and ZLK it is 0.5, which is 50%. And we already determined XW of the light key as 7.4 10 to the power minus 3, and we already determined XD distillate composition of the heavy key, which is again very small, as 0.024. So we have everything ready. We can plug it here, here, here. So you know, you get the idea why we are doing this material balance before. So using calculator, you will get a value of NR over NS is equal to 0.5. Again, this is one equation but two unknowns. How to get these two unknowns? We need another equation. The another equation will be NR plus NS is equal to N, and the total number of stages, we know them from Galilean correlation. The Galilean correlation gives us the total number of stages as 61.9. So this one you can replace this n with 61.9. So you have two equations, two unknowns, you can solve them simultaneously, and after you solve them simultaneously, you will get that n, sorry, you will get that nr is approximately 21 stages in the rectification section, and also you will get ns as around 41 stages in the stripping section, and this includes the reboiler. It is with one stage for the reboiler. So it is like 40 stages in the stripping section and one stage for the reboiler. Okay, so you can say that you have this column. This is the feed here. This is the rectification section. This is the stripping section. So here are the stages for the rectification section, and here are the stages for the stripping section, including the reboiler over there. And if you have a partial condenser, it will be over there, stage itself. So the feed stage, if we have the rectification stages as 21, so you can say that the feed stage is stage 21, for example, which is the last stage in the rectification section. Okay, or you can say that feed stage is the first stage in stripping section. Okay, it's just approximate. That depends whether you count from top to bottom or from bottom to top of the stage. But as a convention, I personally prefer to count stages from up to down. So it will be stage 1, 2, 3, 4, up to you cross the feed stage. So it will be the first stage in the stripping section, or you can use the last stage in the rectification section. So I can say that the feed stage is stage, which stage? Yeah, stage number 22. This is my feed stage. Okay, 22. After I finish 21 rectification stages, the next stage will be my feed stage, and then I start counting for 41 stages for stripping section, including the reboiler. So that's it. This is the problem that we have. So let me summarize it again. So step 1, what we did is that we find the relative volatility. We find the relative volatility for the light key, and for the heavy key, and for the light non-key. And if we have heavy non-key, we will find it, of course, also. Okay, and we find this relative volatilities with respect to who? With respect to the heavy key. Second step, I did a simple material balance. And why I choose specifically this variables to find in the material balance, because they will help me later in the correlations. Like I choose to find, let me summarize the most important variables are like the di, the distillate flow rate for the individual components, like xd for the light key, for the heavy key. It is like also x waste for the light key, for the heavy key. It is like d and waste, and if I didn't miss anything, everything are needed that are needed in the correlations. We need to find them in the second step, which is material balance. Then the third step, I go with Vainsky to find the n minimum. Fourth step, I go with Underwood to find r minimum. Fifth step, I go with Galilean to find the number of stages. And then the sixth step, I use the Kirkbride correlation to find the feed location and the number of stages in stripping and rectification section. So that's it. This problem covers everything that we have discussed before, and yeah, that's it. Thank you for your listening, and I wish you all the best.